Hey guys, welcome to a new PyTorch tutorial. Today we'll be talking about recurrent neural nets, or short RNNs. I will briefly explain the theory behind RNNs and the different kind of applications, and then we will implement a RNN from scratch in PyTorch to do name classification. This should give you a good understanding of how RNNs work internally. So let's start. RNNs are a class of neural networks that allow previous outputs to be used as inputs while having hidden states. Here's an image that shows the architecture of RNNs in the simplest way. So we have an input and then internally do some operations and get hidden states. And then we take those hidden states and put them back into the next step. So we can use the previous knowledge to update our new state. And then at the end, we also get an output. So we can also unfold this graph to get a better understanding. And basically, we are working with a sequence here. So for example, if we have a whole sentence, then we might use every single word as one input. So we have the first input and some initial hidden states. And then we do our operations and get the output and a new hidden state. And then we use this hidden state and then put it into the next input. So we take the next input and use the previous hidden states and again do our operations and get a new output and a new updated hidden state. And then we take the next input and so on. So this is basically the architecture of an RNN. And now, why are RNNs so important? And for this, there is a nice article by Andrei Karpathy. The article is called The Unreasonable Effectiveness of Recurrent Neural Networks. And I highly recommend to give this a read. So I will put the link in the description. But the core takeaway is that RNNs are so exciting because they allow us to operate over sequences of vectors. So with traditional neural nets, we have just a one-to-one relationship. For example, when we do image classification, then our input, so our image, is of fixed length, and also our output is of fixed length. And now with RNNs, we can work with sequences, and there are a lot of different types. So basically we can have a sequence in our input, and we can also have a sequence in our output, or also in both input and output. So for example, we can have a one-to-many relationship where we have only one input. For example, this is used in image captioning. When we have one image and then we want to describe what we see in the image and get multiple outputs. Then we can also have a many-to-one relationship. So we have, this is for example the case in sentiment classification, or what we are doing later with our name classification. So we have a sequence as input and then apply our RNN, and then we use the last output and do some classification with this. Then we can also have a many-to-many relationship. This is, for example, used in machine translation, where we have a whole sentence, for example, in English as an input, and then we put out a whole sentence in French, for example. Then we can also have a many-to-many relationship with a synced way, for example, in video classification, where we want to classify each single frame. So yeah, these are all possible applications of RNNs. So they are mostly used in the fields of natural language processing and speech recognition, but they could, for example, also used for image classification. So yeah, that's what makes RNNs so powerful. And now let's have a brief look at some pros and cons. So the advantages are that we have the possibility of processing inputs of any length. Then our model size is not increasing with the size of the input. Then the computation takes into account historical information, so the previous data. And our weights are shared across time. And some drawbacks are that the computation might be slower than with normal neural nets. and it can be difficult to access information from a long time ago, and we are also not able to consider any future input for the current state. So yeah, that's basically the theory behind RNNs, and now we can directly jump to the code. So in our example, we want to do name classification. So I downloaded the data, and I will also put the link in the description. So basically we have different files with different names. So these are all last names from different countries. For example, we have Arabic, Chinese, Czech, Dutch, English, and so on. So I think these are 18 different countries. And now what we want to do is we want to classify this and detect from which country the name is. And what we're going to do here is we take the whole name as a sequence, and then we use each single letter and put it in our RNN as one input. And for this we need some helper functions. So I already implemented them here, and I will only go briefly through this code. So what we want to do here first, we want to have a helper function to convert our data to ASCII. For example, if we have this name with some special characters, and then we process this, so let's run this file. Then we see it removed the special characters, and we only have ASCII characters left. And basically we also print all the possible letters. So this is from A to C and also in capital letters. And we also allow these signs. And then we have a helper function to load the data. So this basically loads all those files, and then it loads all the names, and it gets the country from the file name. So this is what the load data function will do. And then we have some functions to turn our data to tensor. So we have letter to index and letter to tensor, and also a line to a tensor. And what we are doing here is we are using a technique that is called hot encoding. So we need a way to display our data that can be used for training. And for this, we use hot encoding. So if you've watched my tutorial about the chatbot in PyTorch, then you might already know this. So a hot vector is filled with zeros except for a 1 at the index of the current letter. For example, if we have only 5 possible characters, A, B, C, D, and E, then our A would be a vector of length 5, and we have a 1 at the position where A is. And the same for B, a vector of length 5, and the second index is a 1 and the rest zeros. So this is hot encoding. So if we go back to our file, for example, I can show you how the load data function looks. So this will return a dictionary with the country as key and then the corresponding names as the values. So for example, if we run this and have a look at the key Italian and only take the first 5 entries, then we see we have 5 different Italian names here. Then as I said, we do this hot encoding. So for this, we can use the letter to tensor function. So now if we run this, so let's save this and run this and then print the tensor for J, then we see it has this size. So this is of shape 1 by 57 because we have 57 possible characters. This is what I printed here. These are all the letters. And then we have a J at the position where the capital J is. So this is how our input will look like later. And of course, we do this not only for a single character, but for the whole name. So for this, we have the line to tensor function. And now if here we print the size, so this will be of size 5 by 1 by 57. And the 1 is because our model expects it to be in this shape. And the 5 is because of the number of characters, and the 57 is because of the number of all different characters. Alright, so these are all the helper functions that we need, and of course I will put the code on GitHub, and I also provide the link to the data so you can download these files. So now we can start writing our RNN. So for this, of course, we import the things we need. So we import Torch, we import torch.nn as nn. Then I also want to import matplotlib.pyplot as plt because I want to show you a plot later. Matplotlib. Then we import our utility functions. So I say from utils import all the different letters and also the number of different letters. So this is 57. Then we also say from utils we want to import these helper functions. So load data, then letter to tensor and line to tensor and random training example. So this is basically a function that will do a random choice from those names and return the corresponding country. So now that we have that, we can start implementing our RNN. So we need to have a class and call this RNN, and this should inherit from nn.module as all of our PyTorch models. And by the way, there is already a RNN module available in PyTorch, so you can directly use this, but this is what we are doing in the next tutorial. So for now, we want to implement this from scratch to get a better understanding. So let's have a look at our model architecture again. So this is what our RNN for name classification will look like. So we have an input and a hidden state, and then internally, so this is what we are doing here internally. So we combine them and then we process our combined tensor and we apply two different hidden layers. So we have our input to a output and our input to a hidden layer. So these are just two normal linear layers. And then we get one hidden output and then we use this for the next input. And we also get a output. And since we are doing classification, so a multi-class classification task, we apply the softmax layer and then get the output. So now this is what we want to implement. So now, first of all, of course, we define our init function. This will get self, then it gets the input size. It also gets the hidden size. So this is going to be a hyperparameter that we can specify. And we also get the output size. And in our init function, first we want to call the super RNN and self, and then the init. Then here we want to store our hidden size. So we say self.hiddenSize equals hidden size. Then we define our two different linear layers. So we call this input to hidden I to h equals nn.linear, and the size is the input size plus the hidden size because we combine them. And for this, the output size is still the hidden size. Then we do the same with our output. So we say input to output, and this is going to be a linear layer as well. So the input size is the same. And here we use the output size. And then we also need a softmax layer. So we say self.softmax equals nn.log softmax, and then we say the dimension equals along dimension 1, because our input, for example, just has the shape 1 by 57, so we need the second dimension. So this is our init function. Then we of course also have to define the forward pass. So we say define the forward function, and this gets self, and then it gets an input tensor, and as you should know now, this also gets the hidden tensor. So we use the hidden tensor for the forward pass, and then here we process this. So first thing, let's have a look at this again. We combine our input and our hidden tensor, and then we apply those linear layers and the softmax, and then we return two different tensors, so the output tensor and the new hidden tensor. So let's do this. So let's call this combined equals, and for this we can use torch.cat, and then as a tuple we want to combine the input tensor and the hidden tensor, and here again along dimension 1. Then we apply our linear layer, so we say hidden equals self.I to h, and then here we put in the combined tensor. Then we say our output equals self.I to o with our combined tensor as well. And for the output, we also apply the softmax. So we say output equals self.softmax with the output. And at the end, we return the output first and then the new hidden state. And so this is basically all we need for our RNN implementation. And I'm also going to add a little helper function, and I call this init hidden. So I need some initial hidden state in the beginning. And what I want to do here simply is I want to return an empty tensor. So I say torch.zeros, and this has the shape 1 by self.hidden size. And yeah, so now we can start applying this. So now let's load the data. So let's say our category lines and our all possible categories equals load data. So this is a dictionary with the country as key and the names as values. And this is just a list of all the different countries. And then the number of categories equals the length of all categories. For example, we can print the number of categories. And let's save this for now and see if everything is working. So let's say Python rnn.py. And now this is working. So we see we have 18 different categories. So this is because we have 18 different files here. And now we need to define or set up our RNN. So we say RNN equals, and then we use our RNN class, and this gets the input size, which is the number of possible letters. Then it needs the hidden size, so n hidden, and it needs the output size, and this is the number of categories. And now our hidden size, so n hidden, is an hyperparameter that we can define. So here let's try 128. And now as an example, let's do one single step. So we can, for example, say our input tensor equals, and then we use the letter to tensor function for, let's say, for A, and then we need a hidden tensor. So hidden tensor equals RNN.init hidden. And then we process this. So we say output and next hidden equals RNN with the input tensor and the initial hidden tensor. And now, for example, we could print the output size or shape. And let's also print the next hidden shape or size. And let's run this and see if this is working. So yeah, we see our RNN applied the forward pass, and we get a new output with this shape and a new hidden state with this shape. So it's still the size of the defined hidden size. So this is how it works for only one character. And now if we go back, so now basically we want to treat our name as one sequence, and then each single character is one input. So we repeatedly apply the RNNs for all the characters in the name. And then at the very end, we take the last output and apply the softmax, and then take the one with the highest probability. So this is what we want to do for one name. So now we say we have the whole sequence or the whole name. And here we say our input tensor equals, and then we use line to tensor. And here, for example, we use the name Albert. And then our hidden tensor is the same. And also this call is the same. So we grab this and copy this. And then here we use slicing. So we only use the very first letter now for this simple example. So let's try this and run it and see if this is working. So yeah, so this is working. And now here what we have to do is we have to repeatedly apply these characters. So for this, let's write some helper functions first. So let me comment the print statements out again. So now let's define a function, and let's call this category to category from output, and this gets the output. And as I said, we applied the softmax at the very end. So this is basically a likelihood of each character, of each category. So we want to return the index of the greatest value. So we can get this. So category index equals, and here we can use torch.argmax, and then here we put in the output, and then we can call the .item because this is only one value, and then we can return all categories, the list with this index, category index. So this is one helper function. For example, now if we print the category from output, and then here our output from this name, then if we run it, then we get, now this is Irish, and of course this is not trained yet, so this doesn't look like an Irish name to me. So now what we want to do is we want to train our RNN, of course. So here, as always, we want to set up a criterion and a optimizer. So we say criterion equals, and here we use nn.nll loss. This is the negative log likelihood loss. Then we need to specify a learning rate, and here we have to be careful. So in this case, I try 0.005, and the learning rate is very important here, so you might want to play around with this a little bit. And then we say our optimizer equals torch.optim.sgd, so stochastic gradient descent, and then we want to optimize RNN.parameters, and as a learning rate we use the defined learning rate. So now we have our loss and criterion, and let's define another helper function and call this training. So this is going to be one training step, and this gets a line tensor, so the whole name as a tensor, and it also gets the category tensor. So this is the actual class label or the index of the class label. And now here we want to get a initial hidden state, so we say hidden equals rnn.init hidden, and then as I said, we want to do this repeatedly, so we need a for loop, so we say for I in range and then the length of the line tensor, so we say line tensor dot size and then index 0, so this is the length of the name basically. And then we apply this, so we say output and hidden equals RNN with the line tensor of the current index, so the current character and the previous hidden state. So note that we put in the hidden state and then assign it also to the same variable, so the new hidden state will be the output from the RNN. And then we do this for the whole name, and then for the very last character we get the final output, and then we use this to calculate our loss. So we say loss equals, here we apply our criterion with the output and the category tensor. And then, as always, we do our optimizer steps. So first we say optimizer 0 gradients, then we say loss dot backward, and then we say optimizer dot step. And then at the end of each training step, let's return the output, and let's also return the loss dot item, so not as tensor but as float value. And now we have this helper function for the training step, and now we can do our typical training loop. So for this, let's track some things. So let's say the current loss equals 0 in the beginning, then all losses equals an empty list. So here we want to put in all the losses so we can plot them later. Then let's say our plot steps and also our print steps equals, let's say 1000 and 5000, and the number of iterations equals, let's say 100,000. And then we say for I in range and iters. And now what we want to do is we want to get a random training sample. So we have this as a helper function, and this returns the category, then it returns the actual line or the name, then the category as tensor and also the line as tensor. And we get this by calling the random training example function from the utility class. And this needs the category lines as input and all categories. And then we call the training function. So we say output and loss equals training. And this gets the line tensor and it gets the category tensor. Then we add the loss to our current loss. So we say current loss plus equals loss. And then we want to print some information. So we say if I plus 1 modulo plot steps, so every 1,000 step, if this equals 0. So here we want to calculate the current running loss and append it to all losses. So we say all losses dot append, and here we say current loss divided by the number of plot steps, and then we set our current loss back to 0, because here we add it up for every iteration and then only every 1,000th step we append it. So we have to divide it by the number and then we get the average. And now we do the same with the print steps. So we say if I plus 1 modulo print steps equals 0, then we want print some information. So first we want to get the guess. So we say guess equals category from output, and we put in the output, of course. Then we check if this is correct. So we say correct equals, and then we say correct, and this is correct if the guess equals the actual category that we get from the random training example. And if this is not correct, then we print wrong, and we also want to print the actual category. So let's use this as an F string here, and here let's print the actual category. And then we print as an F string again. We want to print the current iteration step. Then we also let's print I divided by the number of iters times 100. Then let's also print the current loss. So we say loss, and let's print only 4 decimal values. And let's also print the current line. So basically this is the name. And then let's print the guess. And let's also print the if it's correct or not. And now we are done. So this is basically all that we need. And now when we are done, let's plot our losses. So let's create a figure with matplotlib. So pld_lt.figure and plt.plot. And here we want to plot all the losses and then say plot show. And now we could already start our training. And now what we, for example, what we can do is we can save our model here and then use it later or for whatever we want. But in this case, I simply want to try it myself. So I say while true, and then I say I get a sentence as input, and let's say input, and then I put this to a function, or I first, let's say if sentence equals quit, then I break, and otherwise I want to predict the sentence. So for this, let's create another little helper function. Let's call this predict, and this gets the input line, so as raw text. So first of all, I print, let's print a new line, and then let's print the input line as well. So for this, of course, we need an F string. And now here in our prediction, we should use torch.noGrad, so we can turn off the gradients now. And then what we want to do is we want to say our line tensor equals line to tensor from the raw input line. And now we want to do the same as we're doing in our training step. So we have the initial hidden state and then repeatedly apply our RNN. And let's do this. So let me copy this and put it here. So we have the initial hidden state, then we say for I in line tensor size 0. So, and then we get the new output and the new hidden state by applying the RNN. And then at the very end, we want to get the guess. So we say guess equals, and then we say category from output, and we use the last output from the last step. And then we simply want to print the guess here. So in this example, I don't calculate the accuracy or anything. I just print the guess and see if it's correct or not. So yeah, so let's save this and let's run this and hope that everything is working. So this might take a few seconds or minutes. So this is from the first example that I showed you. And now we see we have step, this should be 5,000 actually, and this should be 5% of the training is done. And then we have the loss and we have the name, and we see that the guess is wrong because this is actually Polish. Alright, so now it's done and it's plotting the losses, and you see that it's decreasing very quickly, and then it's trying or jumping around a little bit but still decreasing. I think this is a pretty good result, so let's have a look at some random guesses during the training. So we see that in the beginning almost every guess is wrong, and then it's starting to learn something. So now it's starting to do correct predictions, but of course it's still not perfect, so there are still wrong corrections. But yeah, at the very end we have this loss, so this is pretty good. And now we can try it ourselves. So now, for example, we could go and try some names from those files. So for example, let's start with some German names. So let's try Acker, and we see it says German. So let's try Adler, for example, and this is also correct. So let's try some Italian names. I think these are pretty clear to detect. So let's try Abadelli. And it says Italian, so this is correct. So let's try some Russian, for example. Let's say Abaimov, and it says Russian. Yeah, great. So let's try something more difficult, for example, Chinese. So let's try Bao, and it says correct, Bao. Let's try Bai. Still Chinese, so it looks like it's working pretty nice in this example. Of course, it's still not perfect, but for now all the guesses are correct. So now you see how we can train a RNN to do name classification. And yeah, I hope you enjoyed this tutorial and now know how RNNs can be implemented in PyTorch. If you like this tutorial, then please consider subscribing to the channel and leave me a like, and see you next time. Bye!